Thank you for having me. I'm Porter. I'm here to talk about security and circuit anatomy. Very excited to see you all today. When I was preparing these slides, just a warning, I wasn't sure what the background of the audience was going to be, and so I assumed that there might be more beginners who want to learn how ZK Sync circuits work. There's actually a lot of experts in the room, including some of my teammates who wrote the circuits, and so I will try and make it interesting by talking past what's just on the slides and say some more advanced things so that everyone can learn something. Cool. So my background is I'm on the security team at Matter Labs. I help our cryptographers a lot, working with our auditors and bug bounty programs and things like that. And I like math. So ZK Sync, if you don't already know, it's leading ZK rollup on Ethereum. We are working to advance personal freedom for all. Our one company announcement is we are hyperscaling with the ZK stack. ZK stack is it's actually already been in the works a little bit, but we're announcing it at the conference this week. So it's kind of not related to my presentation, but if you'd like to build with the ZK stack, reach out to our team. But also I want to say the Matter Labs team is like the most amazing team I've ever worked with. If you ever have a chance to come apply and work here, the team is really, really good. There's a lot of smart people, and I really like my job every single day. It's great working with these people. So with that, our mission statement, and then we'll get started. Our purpose is to break financial barriers and enhance the world's freedom by accelerating the mass adoption of public blockchains. It's easy to plop a mission statement on a screen, but everyone at Matter Labs really does believe in this stuff through and through. So today's agenda. Very brief intro on ZK rollups. I know you guys already know what they are, but very, very brief, and then we'll dive deeper into more interesting things. And then what do we need to prove to make a ZK rollup? Circuit anatomy, which is a new buzzword that I've made up for this talk, but it's the structure of how all of our circuits fit together. And I'll talk about security and conclusion. So ZK rollups, what are they? Everybody knows ZK rollups are just rollups that ZK prove everything. And so the question though is what is everything? And I think this is the part where a lot of if you're not as technical or not as into the ZK math itself, this is where most people get lost, is the what is everything? And it can be intimidating because you think that there's no way I'll be able to learn beyond this level because ZK circuits must just be impossibly complicated. That's not really true. We can actually break it down, and hopefully this is going to make a ton of sense, and all of our circuits will be very straightforward to you. So what do we need to prove in general for ZK EVM specifically? We're trying to prove everything that the Ethereum virtual machine does, which is what? Well, it's all the opcodes that are all the operations that you can call. So adding, subtracting, multiplying, dividing, shifting, jumping to another instruction, storage reads. I put that one at the bottom because that one's a little more complicated than some of the others. So when it comes time to make the circuits, we might handle some of these a little bit differently. So we do need to prove also memory and storage. So anything that's read or written to memory or placed in storage for later, we also need to prove that besides just the raw computation. There's also the precompiles to worry about that aren't really opcodes, but you want to call these sort of special syscall functions. EC recover stands for elliptic curve recover. It's how you get back from the signature to the Ethereum address. Ketchak and SHA-256 are common hash functions. We also need to check that we're executing the correct code. So I said earlier that we're going to prove every opcode, but how do I know that those opcodes that I'm proving are actually what was supposed to be there in the first place? Well, we'll need to check that and make sure we're reading that we're executing the correct smart contract. And I think this is lastly, we'll need to prove events and L1 messages. Events are pretty much just L2 messages. It's just little posts of data on the chain so that maybe you can read the chain later and just look through events for something. Cool, so that's all the things that we'll need to prove. Now let's look at how ZK Sync described our circuits. I call them Boojum circuits. Boojum is the name for our new proof system. It's finally coming into production in the next week or two, depending on how fast we roll it out. It's been through a bunch of testing, a bunch of security, and a ton of stuff, and I'll talk about that later. The circuits are written using the Boojum library, so I've just called them the Boojum circuits here. So first of all of the opcodes need to get proven, and this happens in the main VM circuit. This makes a lot of sense. It's the sort of the meat of like proving all the execution is that the I don't know, it makes sense to call it the main VM because it does most of the work. So the way the main VM circuit works is it's going to have multiple cycles, and every cycle will just do exactly one opcode. So we might do one add, and we'll have to prove the add. There's some other details like proving that the registers are updated in the correct way. But if you're new to ZK, you could see how you might be able to prove one add at a time, and then a divide, and then a jump, and keep cycling through, and that's how you work your way through all the proving. Storage read is expensive, so theoretically we could just put everything in one giant circuit, but that's going to hurt performance because some of these operations are very slow, some of them are fast. So pretty much our main VM circuit only does actually the very quick operations such as addition, and then it will also post to another circuit more expensive things such as storage read. So we have other circuits that handle the memory is handled by the RAM permutation circuit, and storage is handled by the storage application circuit. Similarly, we have circuits for all the precompiles. EC recover, catch-act, SHA-256, they all get their own circuits. All of these are very commonly called functions, and so it makes sense to sort of optimize one circuit just for these pieces of code. And also checking that the code that we're executing the right thing. This happens in the code decommitter circuit. And the events in L1 messages are actually so similar that we can put them in the same circuit, and that one's called log sorter. And that's it. So we can put all of our circuits together. If I showed you this diagram at the beginning of the talk, that would have looked terribly complicated. It still might look a little complicated, but I've already explained everything. We start with our main VM circuit at the top. Thankfully, the screen's pretty big, so I think hopefully people can see it. Top middle is main VM circuit, and it pushes things later. So we see on the right the logs, the storage sorter, storage application. On the left-hand side, you'll see things like catch-act and SHA and RAM permutation circuit. And so this is what all of our things look like in practice. Cool. All right, so that's the beginner level. I do want to talk for, I guess I've already been talking a little bit, but talk for a little more detail about really how all this fits together. So it's nice to have a circuit for everything, but you also have to connect them properly. And naively, everything's in all of computer science just connected with a queue of some kind. But we need to make sure that we can also prove that our queue is done correctly to prove that we've actually done everything that we're supposed to pass around. So the way our queue works is basically just a repeated hash of each input, and then in the same way that's when we're pushing into the queue, and then when we pop from the queue, we also repeated hash everything that we pop, and we should end up at the same spot because you're popping all the same elements you're pushing. So at the end, we just have to check that the queue is empty and that all the pushes equal all the pops, and we're good. So that's how our queues sort of hold all of the things together. There's one other caveat that I've slipped past, which is that some of these circuits can only handle a little bit of data at a time. And as we're running our big blockchain and doing tons of transactions at a time, one of these circuits might not actually be enough for an entire batch. And so in practice, we'll actually probably have 10, 20, 100, I don't know, copies of the main VM circuit running next to each other in a row. And so we'll also need to prove that basically the inputs to one VM circuit are the same as the outputs from the previous one. So just chaining everything together nicely. So you do all this, and then you recursively prove all the multiple copies of the main VM circuit down to one, and then we have a scheduler circuit which finally wraps all of these things together. And at the end, we end up with one final proof, and that is the outline of ZK Sync circuits. So we did it. All right, the second half of the talk is about security. So there's about $450 million TVL on our blockchain right now. And so the second half, I'm on the security team. I have to keep this safe. And I also want to get some sleep at night. So how do I do that? It's a tough job because sometimes if you miss one line of code, then there can be very catastrophic damage and extra things can get proved. I will give one caveat to this, which is that just breaking our proof system is not always enough to actually get an exploit in the production system, because we have some like defense in depth measures outside of just the like ZK cryptography. But for this talk, I'm just talking about like the ZK cryptography itself, and we don't want any bugs. Also, Chainlight's in the audience. They wrote an awesome write-up of this bug and how it happened and full explanation. Thank you, Chainlight. So, ZK audits. We work with individual auditors and companies like Trailbits, Spearbit, Chainlight, several others. These people are amazing, tons of domain experts who have spent a lot of time looking at this type of stuff. It's super great working with them, especially when we have like one piece of the code base that we really want someone to look at. Like if we like completely rewrite one of the circuits to, like, for instance, we recently rewrote Easy Recover for performance reasons because it's called so often for every single EVM transaction. So now that we have like a super optimized one, we're going to want like a new audit for that. Competitive audits are very fun. We recently gave away, well, in the process, I guess, of giving away $1.1 million USDC with Code Farina. I think it's the largest competitive audit on Code Farina ever. It was also the first ever audit on Code Farina that included the ZK circuits, so that was a big deal. If you helped to look at our code, I might have answered some of your questions. I helped write some of the documentation. Hopefully that was useful. And it's pretty fun to get to give away like this much money in 3 weeks. And a lot of amazing people came together and like found some cool bugs, which will be announced soon, I think. We've finished judging, and all the bugs were submitted, and we fixed all the errors already, but we're waiting for Code Farina to decide like how much money each person gets. So that's the holdup if you're waiting on your bounties. But we'll probably continue to do more competitive audits in the future, so if you missed this one, there will be more chances because the results we get from this are actually really amazing, even compared to traditional audit firms. Bug bounty is always ongoing, so if anything happens, if we've missed anything, and we will reward you if you come submit a bug to us at any time. And one announcement that I can start to say is that we are working on adding, not just our circuits are in the bug bounty now, but the compiler will also be added to the bug bounty, and I think this is going to be the first compiler that's on Immunify. So we're working through some like challenges of like how do you include this type of code, and how will we like check bugs, and so it's very exciting to be able to put like so much of our code base on Immunify. It's awesome. A few more techniques for circuits is fuzzing, formal verification, and something that we are working on and like have like very solid progress is two-factor authentication using TEs. So this is something that's very cool. I think Justin Drake wrote a blog post about this on ETH Research like a year ago, but you can double check whether the ZK proof was done correctly by running all of the same code, or not the ZK code, but just normal code inside a trusted execution environment, and only when both of them agree on the output, then you move the chain forward. This way, even if there's some critical circuit bug, as long as like the TEs don't have the same bug, it won't break the chain and people won't be able to steal money. And so our TE engineers are like super talented people. I actually get to work with them a lot. Very excited for this. So cool. I think that brings it to the end. So thank you. If you want to learn more, message me on Twitter anytime. I always answer questions. And it's great to be here. We have time for questions?
Thank you for your presentation. And I have questions. You mentioned why storage read is expensive.
Yeah, why storage read is expensive. That's good. So it's because of the way like it comes down to how the proof system works, which is like, I didn't want to go too much into Boojum. We're using Plonk arithmetization with Fry prover, if that means something. And basically to do like normal arithmetic, it's easy to just make Plonk gates and constraints. To do a storage read, a lot of times you want to do like a permutation argument, and so that permutation argument can be like larger and it's kind of different and unique, so it doesn't quite make sense to fit it in with the rest of the opcodes. But that leads to a bigger point, which is that some operations like L1 gas costs are like how expensive it is to do an L1 operation, but some L2 gas costs can be different because like some things are easier to prove, some things are harder to prove. So that's kind of an ongoing challenge, is how do we like line up the costs between the two. Thanks. Okay, I'll stick around afterwards. Thank you guys.